So at this point, we've talked about the dot product and the cross product, and we've defined each of them and we've learned how to calculate both of them. But in this video, we really want to talk about what they mean and how they represent really opposite ideas. So let's start by talking about the dot product side of things. And the dot product really measures how much two vectors move in the same direction, or how much they point in the same direction. And we can really see that if we look at the formula for the angle between two vectors. So remember that we said that the angle between two vectors was theta. In the formula here, where we have the two vectors, we take their dot product. So we have the dot product of the vectors A and B, and that's equal to the product of the lengths of these vectors. So the length of A multiplied by the length of B, and then we multiply that right-hand side by cosine of theta, and theta is the angle between the vectors A and B. And so we really see the value of the dot product if we pick different values for theta. So let's start with perpendicular or orthogonal vectors. When two vectors are perpendicular, the angle between them is 90 degrees. So we'll say theta is 90 degrees. And when we evaluate this angle between vectors formula at theta equals 90 degrees, we get cosine of 90 degrees. That value is 0, which means the entire right-hand side is going to be zeroed out, which means we're saying that the dot product of A and B is equal to 0. If we look at theta equals 0 degrees, and in that instance, the vectors would point in exactly the same direction, because if they're pointing in the same direction, the angle between them is going to be 0. When we plug 0 degrees into this formula, cosine of 0 is 1, which means the dot product really just simplifies down to the product of the lengths of the vectors. So the product of the length of A and the length of B. And if we choose theta equals 180 degrees, if we choose 180 degrees, that means the vectors point in exactly opposite directions. So if we wanted to illustrate this here, for this first example, let's say we have the vector like this that's blue, and then the vector like this that's yellow. We're calling these A and B here, so that's what theta equals 90 degrees would look like. For theta equals 0 degrees, we would have something like this, where we have the blue vector, and then the yellow vector is sitting right on top of it. They point in exactly the same direction. Or we could have something like this, where we have the yellow vector here. They point in the same direction either way. And then for theta equals 180 degrees, we have the blue vector, again pointing in this direction, but then the yellow vector will point in exactly the opposite direction. So that's theta equals 180 degrees. And in that case, cosine of 180 degrees is -1. So the dot product here simplifies to the product of the lengths of the vectors, but multiplied by -1. So we get negative, and then the length of A multiplied by the length of B. So what we see then is that when we have orthogonal vectors, the dot product is always going to be 0. When we have vectors that point in exactly the same direction, the dot product will just be the product of the lengths of the vectors. And then if we have vectors that point in exactly opposite directions, the dot product will be the lengths of the vectors multiplied by -1. So let's just make up an example, and let's say that the length of vector A is 5, and that the length of vector B is 2. If that's the case, if A and B were orthogonal to each other, their dot product would be 0. If A and B point in exactly the same direction, their dot product would be 10. And if A and B point in exactly opposite directions, their dot product will be -10. So you can see that the dot product is really minimized when the vectors point in exactly opposite directions. If they point in exactly the same direction, then their dot product is maximized. And if they're orthogonal, then the dot product is 0. And if we kind of sketch this out in the plane here, to sort of get an idea of what this would look like, let's say that the vector A points exactly toward the positive direction of the x-axis. And then let's sketch out some examples of vector b. So we could have the vector b that points in the same direction. We could have the vector b that points orthogonal to a. We could have the vector b that points in exactly the opposite direction. And then we could have some sort of in-between values like this. So we could have vector b that points this way and vector b that points somewhere right about there. Not exactly the same direction, not exactly the opposite direction, but not orthogonal either. Right at this point right here, we said the dot product is just going to be the product of the lengths of the two vectors. And right at this point right here, we said the dot product is going to be the negative product of the lengths of the vectors. Right at this point right here, the dot product will be 0. At this point right here, because the vectors are pointing more in the same direction than they are in opposite directions, in other words, because I'm less than a 90-degree angle here, I know that the dot product is going to be positive, but it's going to be less than this value we would get here if they pointed in exactly the same direction, and greater than 0. So that's going to be a positive value. At this point right here, if that's the vector b, then the dot product is going to be a negative value because the angle between the two vectors is still greater than 90 degrees, so more or less these vectors are pointing in different directions. But again, if my value here where they point in exactly opposite directions, 180-degree angle between them, if that were negative 10 and this value is 0, then this vector right here is going to be somewhere between 0 and negative 10. Maybe it's negative 5 or something like that. But that's how we want to imagine different values of the dot product. Now, the cross product is sort of the opposite idea. It measures how much two vectors move in different directions. So if the dot product measures how much the two vectors move in the same direction, the cross product measures how much they move in different directions. The cross product formula we use, again, if we stick with the same vectors a and b, we use this formula here. We say that the length of the cross product, so a and b, that's the length of the cross product there, is equal to the product of their lengths, so the length of a multiplied by the length of b, and then we multiply that by sine of theta, where theta is the angle between them. So let's again look at some of these values. We'll start with the orthogonal case where theta is equal to 90 degrees. So at 90 degrees, sine of 90 degrees is always 1, which means that we can say that the length of the cross product is equal to just the product of the lengths of the individual vectors. So the length of A times the length of B, because sine of theta, sine of 90 degrees, simplifies to 1. When the angle between the vectors is 0, so for theta equals 0 degrees, sine of theta is 0. Sine of 0 degrees is always 0, which means we're going to zero out the right-hand side, and so we're going to say that the length of the cross product is going to be equal to 0. And if we look at theta equals 180 degrees, if the vectors point in exactly opposite directions, sine of 180 degrees is always 0. So again, I'm going to zero out the right-hand side, and I'm going to say that the length of the cross product is 0. So what we're really concluding here about the cross product is that when the vectors are collinear, when they either point in exactly the same direction here, or when they point in exactly the opposite direction, so again, that looks like vectors like this. We have vectors that point this way, and then either when the vectors point in exactly the same direction, or when the vectors point in exactly opposite directions, in either case, they're collinear or they're parallel. In both of those cases, the length of the cross product vector is going to be 0. But when the vectors are orthogonal, when they're perpendicular, the length of the cross product is going to be maximized. It's just going to be the product of the individual lengths. So again, if we take the same example here where we say that the length of the vector A is 5 and that the length of the vector B is 2, then if the vectors A and B were orthogonal or perpendicular, then the length of the cross product is going to be 10. But if they happen to be collinear, either pointing in the same direction or in opposite directions, the length of the cross product vector is going to be 0. So again, if we sketch that, if we sort of sketch out our axes like we did for the dot product, so something like this, if we say this is our vector A that points in this direction, and then we have these different possibilities for B, so B could either point in the same direction, it could be orthogonal, it could point in exactly the opposite direction, or it could point somewhere somewhat in the same direction or somewhat in the opposite direction. Neither one of these is orthogonal, but neither one is exactly the same direction or exactly the opposite direction. So we know that in this case, when the vectors point in the same direction, the length of the cross product is 0. When they point in exactly opposite directions, the length of the cross product is 0. When they're orthogonal to each other, up here, we know that the length of the cross product is the product of the lengths. And that's always going to be a positive value because lengths are always positive. So that's always going to be a positive product there for the cross product length. And then for both of these points, so if you have a case like this where the vectors point somewhat in the same direction, you're still going to have a positive value for the length of the cross product because again, we're talking about a length. It's just not going to be as large of a value as if the vectors were orthogonal. So again, going back to this case here, when the vectors are orthogonal, the length of the cross product would be 10. Down here, where they move somewhat in the same direction, maybe the length of the cross product would be 5. And then the same thing over here, if the vectors move in somewhat different directions, of course you're still going to have a positive length because length has to be a positive value, but the length of the cross product won't be as great as up here when the vectors are orthogonal, because here when the vectors are orthogonal is when the cross product is maximized. So when we say that the dot product is kind of about how much the vectors move in the same direction, that's because we have this value here for the dot product of the lengths of the two vectors when they move in exactly the same direction, and then when they move in exactly opposite directions, we have this negative product of the lengths. And we say that the cross product is kind of a measure of how much the vectors move in opposite directions because we have this product of the lengths of the two vectors when the vectors are orthogonal, when they're at 90 degrees. But ultimately, if you can remember these values here, or you can think of, by plugging into this angle between vectors formula, if you can remember that the dot product of orthogonal vectors is 0, and that you have the product of the lengths or the negative product of the lengths when they move in the same or opposite directions, and then these values here as well, that the length of the cross product is maximized for orthogonal vectors, and that for collinear vectors, the length of the cross product is 0. Those are the key things that you want to take away so that you can quickly think about the values of the dot and cross products for any two vectors, A and B.